Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff, the great stuff. This is the AAS Journal Author Series. And I am super happy to have Sofía Burne with us today. Hello, Sofía.
Hi, everyone. Hi, Frank. Thank you for having me.
Well, thanks for agreeing to talk about your very awesome article here. We're going to get to that soon, but it's very cool. And Sofía, what's your geolocation? Where are you located at?
I'm in Buenos Aires, Argentina.
All right, so we are in the south today. Very cool.
Yeah.
So it is June 28th of 2023 as we record this. So you are in your winter.
Right.
Yeah, and I'm in Phoenix, and we are very definitely in our summer here. The power switch is thrown. We are hot.
We're quite warm today here, so
Yeah, very cool.
a fake winter.
Does it rain much in Buenos Aires in the winter?
Not so much in the winter, but more in the fall.
Oh, in the fall. Okay, so that's the wet season. Okay.
Yeah.
Very cool. Very cool. And what's your position there in Buenos Aires? where are you at?
I'm working at an institute called IAFE, that in English it would be Institute of Astronomy and Space Physics, I think.
Good enough.
That depends on the University of Buenos Aires.
Okay, very nice. Awesome. And Sofía, what do you like to do for research?
Well, actually, I'm in my last year of my PhD program. And throughout my PhD, I mainly focused on studying the interaction between some planetary systems and the solar wind. More precisely, there's a plasma boundary called the Bauschak region that forms in front of some planets and some moons, and is the responsible of slowing down the supersonic solar wind and letting it know that there's an obstacle behind. So that's my main focus throughout my PhD. And also, I've been mainly interested in studying unmagnetized bodies, such as Mars and Titan.
Very nice. Very nice. Well, congratulations, Dr. Sofía.
Not yet.
Close enough. I will give you your honorary PhD after.
Oh, thank you.
Practice for your defense talk or something like that.
Right.
Very cool. And that is going to bring us to this very awesome APJ article. It's open access, people. We're in the open access era. You can go get a copy for free. Go grab one. Space weather in the Saturn-Titan system. And Sofía, take us away.
Okay. Well, first, a shout out to my colleagues. I have done this work with my supervisor, Cesar Bertucci and Laura Morales. But I also work with some other awesome colleagues like Nick Sergis, Nicolás Aquilos, Beatriz Sánchez Cano, Yairesca Collado Vega, Sergio Dasso, Niklas Edberg, and Bill Kurt.
Very
so
good.
A couple of us.
Great shout out. Great shout out.
So in this work, mainly what we did was study the plasma environment with Cassini data around Saturn and Titan from late November 2013 to early December. And this includes Cassini's T96 flyby to Titan.
Ooh, right.
That has that flyby took place on December 1st.
Okay.
And it includes the only observation today of Titan, the moon, exposed in the solar wind. Okay. It's a very interesting data set.
Indeed.
Yeah.
Indeed. Very cool.
What we did basically was study the plasma environment and try to find out how this scenario took place. How is it that Titan was found outside of Saturn's magnetosphere? Okay. So this took us to a space weather study that is usually related to the study of solar phenomena on Earth, like ICMEs or co-rotating interaction regions, CIRs. But more recently, it's being used to study other planetary environments. And there's an increase in... Oh, sorry, I missed you there.
That's okay. I'm just... It's all good.
Now, and recently, there's more and more studies that focus on studying maybe the evolution of ICMEs across the heliosphere, or how these extreme events impact other atmospheres different from that of Earth.
Cool.
Well, yeah, and in the case of Titan, that's a very interesting, well, moon, not planet, but it's a very interesting obstacle to study, because not only is the second largest moon of the solar system, the largest for the Saturnian system, but yeah, it's quite large to be a moon, but also it's the only moon. It's the only moon from the solar system that has a optically thick atmosphere.
Mm-hmm.
And it's actually said to resemble the atmosphere of early Earth.
Ooh, okay.
So in many ways, it's also similar to Mars because of its size and the lack of an intrinsic magnetic field. But in other ways, it has similarities with planet Earth.
Okay, nice.
So this Titan usually no, it always orbits Saturn at around 20.2 Saturn radii.
Okay.
One Saturn radii is a little more than 60,000 kilometers.
Okay.
And well, Titan's orbit usually falls completely inside Saturn's magnetosphere.
Okay. Yes. Yes.
So the moon usually interacts with the planetary plasma. That is, it interacts in a regime that is submagnetosonic and subalphenic.
Okay.
So that would be a different plasma interaction expected from the supermagnetosonic and superalphenic solar wind.
Yes.
And well, when there's increases in the solar wind dynamic pressure, Saturn's magnetosphere can compress, and Titan has been observed outside of what's called the magnetopause of Saturn. So outside that plasma boundary, but within, still within the magnetosphere itself, in the magnetosheath.
Okay.
But only during this flyby T96 was it observed completely outside of Saturn's magnetosphere and in the solar wind.
Nice. Very nice.
And well,
was that planned or was that fortuitous? Did that just happen, or was that a planned event?
No, that just happened.
It's serendipitous. Okay, cool.
Yeah. It would have been cool if it happened more than once.
Lightning strikes twice.
Yeah. So in 2015, Cesar, my supervisor, published an article about this T96 observation of Titan in the solar wind, and found that because it lacks an intrinsic magnetic field, the way it interacted with the solar wind was forming a collisionless bow shock and an induced magnetosphere from the pileup of the interplanetary magnetic field that drapes around the ionospheric obstacle that is the moon.
Got it. Cool. That's cool.
So that is very similar to what happens at Mars and at Venus, for example.
Oh, Venus, yes.
Yeah, and also around this period of time, there was an article published by Elias Roussos in 2018, where he reported a very great catalog of solar energetic particle events and, well, other type of events that are modulations of the galactic cosmic rays with periodicities of solar periodicity. Okay. All along Cassini's mission. And among all of these events, there was one SEP event, one solar energetic particle event, that took place around the time of T96. So there was all of these things going on that was very interesting to study more in depth.
See, lightning did strike twice. You got two.
So if you want to go, I don't know, maybe to figure 2, because figure 1 can be skipped, similar to.
Sure. Let's go zenith angle. Okay, let's go figure. Nice table there. Figure 2. Here we go. Let's go. Okay, let's get a global on this one, and I'll zoom in as need be. Okay.
Yeah. So what we did first was study, we say, the dynamic evolution of both Saturn's magnetopause and bow shock. So we wanted to study how it changed throughout the days, both prior and after the T96 flyby. So here we have in the first panel, panel A, the magnetic field measurement by Cassini's flash-gate magnetometer from November 26 to December 4. Remember, the flyby was on December 1st. So here in orange, there, perfect, you have what we label TCA for Titan's closest approach. That is the closest approach between the spacecraft and the moon during this flyby.
That's the orange line, the vertical. Okay.
And well, in the different shadings, we have the regions where the spacecraft is in Saturn's magnetosphere in green.
Okay.
In pink, we have when Cassini is in the magnetosheath, and in white when it's in the solar wind. So we see that throughout all of these days, the spacecraft crossed these plasma boundaries multiple times.
Yeah.
It was a clean solar wind observation. And we see that from the passage from the magnetosheath to from the magnetosphere to the magnetosheath, we have the Saturn's magnetopause crossings that we label MP, MP1, MP2, MP3, etc.
Yes. Okay, good.
Later.
I'm with you.
From the passage from the magnetosheath to the solar wind, we have the crossings of Saturn's bow shock, BS.
Yes. Got it.
And we well, basically we see that from November 26 to November 27, Cassini crosses the magnetopause 3 times.
Yes.
And from late November 28 onwards, it crosses Saturn's bow shock multiple times.
Yeah.
So many that we didn't label them with numbers.
Yeah, it's too many of them, but yeah.
Then it finally encounters Titan on December 1st with this vertical yellow-orange line.
Yes.
After Titan, it crosses Saturn's bow shock other 3 more times, and it stays in the magnetosheath for a while until it crosses the magnetopause for a 4th time.
Yes, very cool. Okay, I'm with you.
Okay, so what the other panel shows are the panel B. We have the estimated solar wind dynamic pressure.
Okay.
What happened here is that Cassini had an instrument called CAPS, the Cassini's plasma spectrometer, but unfortunately it broke down around 2012. So for these observations that took place in 2013, we didn't have in situ measurements of some of the properties of the solar wind, like the pressure, for instance, or maybe the bulk speed or the density of the protons. So yeah, we missed a lot of data. But luckily, we could turn to statistical empirical models that associate the position of Saturn's bow shock or magnetopause, there are different models for each, with the external, with the solar wind dynamic pressure. So for a certain pressure, you expect these boundaries to be positioned in a particular way. Coordinate, right. So the panel C shows these positions of either the bow shock or the MP, depending on the observation that corresponds. What we plot is the standoff distance, standoff D, that is the position of the nose, the subsolar point of the boundary. That's like the outmost, I don't know how to say, like the most external point of the boundary.
I understand. Yeah. Okay.
So these positions are correlated with the pressures. And actually the models should be used locally when you have the actual observation. But because here in the multiple bow shock crossings, we had so many crossings in such a short amount of time, we took advantage of that and extrapolated the results to draw a curve beyond the actual crossings.
Yes.
So
here. Right there.
In the last panel, you also see it looks like a horizontal line, but it's not actually a straight line. And that's the position of Titan, the distance of Titan to Saturn. That's around 20.2 Saturn radii.
Oh, this one. Okay.
Yeah.
Okay. Ah. Okay. Good.
So, yeah. Basically, the other three plots are complementary, but you can get the idea from these three panels, from the three horizontal panels. What we see here basically is that from November 26 to November 27, when we have the three crossings of the magnetopause,
yes.
We have pressure values that are below 0.02 nanopascals. And we have a standoff distance of the magnetopause that are around 23 Saturn radii. And you see that Titan's distance from Saturn in the last panel is behind the magnetopause boundary. It's a shorter distance than the standoff point of the boundary.
Right. Okay.
So this means that at least
yeah.
around these days, there was not unusual compression of Saturn's magnetosphere.
Fair enough.
But when we start to see the Boschke crossings on late November 28, we see that in panel B, we see that the pressures jump an order of magnitude higher at about 0.1 up to 0.15 nanopascals closer to Titan.
Okay. Okay.
And in panel C, we see that this correlates with standoff distance of around, I think we get up to 19 Saturn radii for the Boschke. Yeah, and you see how Titan goes from being in the magnetosheath, so past the magnetopause, but behind the Boschke, to finally at some point crossing the Boschke as well. Cool. And this includes, and this happens within the observation of Titan by Cassini. That's the vertical line. Nice. Very cool. Okay, and so after Titan, we see that the pressure values continue to go up a little bit. Well, we don't have, around December 3, we have the last magnetopause crossings that has associated solar wind dynamic pressures of 0.15, 0.3 nanopascals, depending on the model you use. Okay. And we don't see Titan anymore with the spacecraft, but you can assume that it might be still outside in the solar wind. Right. So the summary for this figure is that at least from late November 28 and maybe past December 4, there's a big compression of the magnetosphere. Yes. Okay. Okay, so if you want to go down to the next figure, I think. Sure, I'm with you. Okay, observation IMCE, IMCE1, IMCE2, and ooh, this is a rich figure. Here we go, IACEM. Get ready. Okay. So what happened is that during that interval from late November 28 to December 4 at least, we saw signatures that indicated the presence of two ICMEs. Okay. So these two ICMEs could be responsible for causing this unusual compression of Saturn's magnetosphere. Okay. In this figure 3, we have the signatures that show the presence of what we call ICME1. Okay. From late November 28 to late November 30. So this is before Titan's encounter. Titan could be like outside of this plot. Yes. In the first 3 panels, we have magnetic field data. And the first indicator of the presence of this ICME is an interplanetary shock that actually was first reported by Roussos in his catalog of SEP events. That's and yeah, and he reported that this interplanetary shock was responsible for SEP's acceleration, for solar injected particles acceleration. And that is what we actually see in panels D and E that show fluxes of energetic protons. Panel D shows protons in the range of MeV, and panel E shows proton fluxes in the range of KEVs. And we see that there's an increase along the interplanetary shock that even though it's observed inside Saturn's magnetosheath and not in the solar wind, which is unusual, it's still easy to identify it because of the increase in the magnetic field magnitude in the top panel.
Yes.
And the rotations in its components. In the next two panels, you see the rotation.
Data fly.
After the interplanetary shock, Cassini goes out into the solar wind, and we get to measure the interplanetary magnetic field this time.
Good.
And we see values that are above 1 nanotesla, and that is very unusual at 10 astronomic units, where you expect, well, it's difficult to tell with the log scale, but
yeah, well, yeah, I get it. Yeah.
But those values are unusual at these heliocentric distances, where you expect much lower values of around 0.1, 0.3 nanoteslas.
Okay.
So it's, though it doesn't look like much, it is a lot.
Well, yeah, it's a
yeah.
ratio is large and it's a log scale. So yes.
Yeah, here it's difficult because as we have the crossings into the magnetosheath across the bow shocks, you have to show the increases of the field of the planetary field and also the variabilities of the interplanetary magnetic field that are quite different ranges.
Yeah, right. Okay.
But what also comes with this shock, apart from the increase in the magnetic field, is both, well, in panel F, we see this is a proxy of galactic cosmic ray fluxes.
Oh, okay.
It's actually the count rates of one of Cassini's LEMS measurements. LEMS is designed to measure both the energetic protons of the panels above and energetic electrons. And this channel, E6, was designed to detect energetic electrons. But here, the measurements were dominated by galactic cosmic ray protons. Okay. So we have to go back to the raw data, to the count rates, because the flux conversion was not straightforward.
Right, well, dicey.
Yeah, so here what we show is a proxy of galactic cosmic ray fluxes, to say it in some way.
Yes.
And we see that there's a decrease that's associated with a Forbush decrease. We see that and well, a Forbush decrease is an indicator of the passage of an ICME.
Okay.
And besides that, we also have in the panels G and H, we see a perturbation in some radio emissions that are called SKR, or Saturn kilometric radiation emissions, that are radio emissions emitted by electrons that travel around aurora magnetic field lines.
Right.
So these emissions are indicators of also extreme events, because they reflect changes in the configuration of Saturn's magnetosphere. And the main drivers of these changes are increases in solar wind dynamic pressure. And if you see, well, besides the clear perturbations seen in panel H, in panel G, in panel H, we plot the total emitted power, and we see that after the shock, there's an increase that reaches up to 2 orders of magnitude more than the typical values for Saturn.
Indeed, yeah, there's 4 orders of magnitude there. Yeah,
And this keeps increasing when we enter what we marked as the ICME ejecta.
Okay. The
different boundaries we identify by the observation of increases in the field, rotations in the components, and, well, these indirect observations of the radio emissions, the galactic cosmic ray deflection and fluxes decrease. Yeah. Well, all of these gave us an idea of each of the ICME's structure. Of course, this is quite complex. It's not as easy as identifying them at 1 astronomic unit with solar wind data. So we did our best.
Indeed. It's beautiful. It's beautiful.
And, well, around the end of the plot, more or less 10 p.m. on November 30, we see that the interplanetary magnetic field goes down to more typical values of 0.3, 0.5 nanotesla, and we say, okay, here there's normal signatures of this ICME.
Very good. I see it. Okay.
And well, if we go to the next plot.
Okay, I am with you. Okay, that's ICM1, and I bet this is IMCE.
Yeah. So this is actually a zooming of the whole structure of the second ICME.
Okay.
That we see just 2.5 hours after the end of the first ICME. So we have here November, this plot starts on November 30, 11 p.m. And I said the previous ICME, we marked its end at around 10 p.m.
Yes. Okay. Okay.
So
2 in a row. Okay.
Yeah, well, here the analysis we did is pretty similar in many ways. Like we observed the same parameters to identify the different structures.
Yeah.
And there's also the first marker of the ICME presence is an interplanetary shock. But what's different here is that we see Titan's magnetic signature that we mark here in orange. Titan magnetic signature is what we call that is constituted by its bow shock, the one I reported that I said that I reported in 2015.
That's
its bow shock and its induced magnetosphere boundary, both in the inbound leg and in the outbound leg. So all of this is shaded in orange. All of these is quite comprised in this plot.
Right. Cool. Cool.
And we see that the second interplanetary shock is observed just there. It's observed just a couple of minutes, I think less than an hour before the encounter with Titan.
Okay.
And if you see here, the values of the interplanetary magnetic field that reach up to 2 nanoteslas here stay at those high values even after Titan is passed.
Yeah, that's curious. Okay.
So that gave us an idea that maybe when Titan's induced magnetosphere was formed, it was the result of the interaction not with the pristine solar wind, but actually with one of these ICMEs.
Okay. Yeah.
So yeah, if you see the time series, maybe you think, yeah, that's obvious because of the time simultaneity. But it's not so obvious because in 2008, Cesar published a different article about Titan's magnetosphere within Saturn's environment. And he showed that it had magnetic memory. So it showed that the field that forms Titan's induced magnetosphere could pile up a magnetic field that was up to 3 hours old. So that means that what we see with the spacecraft maybe is the result of an interaction with an older field.
Yes. Nice.
So we wanted to explore this. And I won't go into detail about this, but we actually tried to track down these ICMEs back to their solar sources, and we find some potential candidates, but maybe that's better for the end because we have to do more work about that. So I won't go into detail. But going back to Titan's interaction with the solar wind, we can go to the next section of the paper.
4, and then we got
still the CME.
5. This is ICME2. Yes.
Yeah, the other one was a zoom in because this is quite large and you can see it properly.
Right. Should we go on, or do you want to cover this one?
No, it's pretty similar to the other one.
Right. And just a little zoom out. Okay. We got the bees and nice illustration there. Field data. Okay.
So in this section, we tried to study the interaction of Titan with the solar wind. I said that there's already a paper about this, but now that we know that there were these ICMEs present and that the field it was interacting with maybe wasn't the expected pristine solar wind. We have a little more to say about it.
Right. Okay.
And well, these plots show what's called the drop coordinate system. You see here in panel E, there's a sketch from Neubauer's 2006 paper, where he models the pileup and draping of the external magnetic field to form the induced magnetosphere of Titan. That can be either the planetary plasma from Saturn, or in this case, the solar wind.
Right. Okay.
But there's an expected morphology that's associated to the field it's interacting with. So this drop coordinate system is derived by first saying with which magnetic field is Titan interacting with. What is the field that is piling up along the obstacle and forming this induced magnetosphere? So you have to make a guess, or maybe you know, but in this case, a guess, and say, okay, I think the moon is interacting with this plasma of,
good guess.
According to the observations you have. And what we did was suppose that Titan was, that the plasma that generates Titan's induced magnetosphere came from the period after the second interplanetary shock.
Okay.
So we took as the background field the shocked plasma by the second interplanetary shock. That this would be part of the second ICME structure because it's part of the sheath of this shock.
Okay.
And well, we obtain the drop coordinate system, and in the different panels, we try to study the behavior of either the magnetic field along the Cassini's orbit during T96. So in panel A, you have the behavior of the magnetic field magnitude in the C-drop, X-drop plane. To give you an idea, the C-drop axis points anti-parallel to the background field component perpendicular to the flow. Yes. So if you in this panel you draw the magnetic field component perpendicular to the solar wind, it could be pointing south.
Okay.
And then the x-axis, as shown in the drawing, is parallel to the solar wind flow. So is anti-sunward.
Yes. Okay.
And well, basically, on all of these pictures, what we see is that there's, I will go into a little more detail, but we see is that there's a pretty good agreement between the expected morphology of a general induced magnetosphere of Titan and the magnetic pileup and draping morphology we obtain with the observations we measure. So for example, here, let's go to panel, I don't know, panel A maybe.
Let's take a look at A.
It's the simplest of all. I mean, the combination of them is, of course, more important, but here you see, for example, that you have a more intense field towards the center.
Yes.
And that is, how do you say? It agrees with, what's the word?
Consistent?
Consistent, that was it.
Yeah.
Consistent.
Yeah, I'm following.
It's consistent with the fact that towards the nose of the obstacle, there's more pileup of the magnetic field lines, and well, of course, the magnitude of the field becomes higher. And also, if you will go towards smaller values of, well, values of x closer to 0, you are getting closer to Titan, and you also see that the how do you say, the loss of the intensity of the magnetic field is slower than in the upper values of Z, because you're getting closer to the obstacle.
Yeah. Okay.
Well, I don't know if maybe it's too much to go for each panel, but the idea is that in each component, you see the expected draping of the magnetic field lines. You see the behavior that you expect following this model from Neubauer.
Yeah. Ooh, here's a curious one. What is this? Oh, that's why. Okay.
Yeah.
Goes
So
okay.
this made us think that maybe, that
Change direction.
well, maybe there was not fossilized fields from hours ago, but rather almost simultaneous observation of the signature and the field that caused that signature.
Okay.
And that comes from the background field shocked by the second interplanetary shock.
Okay. Okay.
And well, we went a little further to analyze this. And in the next plot, what we did was,
there we go, compatibility.
well, what we did here was plot the magnetic field magnitude and its components, plus its orientation based on the magnetic field clock angle. And in the horizontal stripes, you have the average values of these magnitudes calculated in what's called the magnetic pileup region of Titan's induced magnetosphere. That's the region where there's the most pileup of the magnetic field and the strongest magnetic field pressure.
Mm-hmm.
And
what is the clock angle? What is the angle of what?
The clock angle is the arc tangent of BZ over BY.
BZ over BY. Okay, I'm good. Mm-hmm. Mm-hmm.
So basically here what we saw is that the orientation of the field that is piled up in Titan's induced magnetosphere shared its orientation with the field that is shocked by the second interplanetary shock. If you see here after midnight, on December 1st, after midnight, you see the clock angle is the same as in the average straight stripe. The
pink stripe, I guess you call it.
Okay. It varies quite a lot during the solar wind incursion, but there you have quite stability and you share the same orientation. And that is very important because the configuration of the induced magnetosphere is directly linked to the orientation of the interplanetary magnetic field.
Yeah.
So it's another indicator that Titan is interacting with a perturbed solar wind that is seen in this interval of time.
Very cool.
And well, the last image also tries to contribute to this result, studying the pressure balance.
Okay.
If maybe we can concentrate on the black and the purple curves. The black curve is the in situ magnetic field pressure.
Okay.
And the purple curve is the estimated solar wind dynamic pressure obtained within this magnetic pileup region. Okay. With it's obtained with the balance equation that comes from Spreitzer and Sahara's 1992 paper that relates the maximum magnetic pressure of the pileup field in a general induced magnetosphere with the external dynamic pressure of the solar wind. Because these are like the two most the two most important contributing factors that play a role in the balance that creates these magnetopause, induced magnetopause.
Got it. Okay, got it.
So basically what we see here is that the measured magnetic field pressure balanced with expected solar wind dynamic pressure of about 0.35 nanopascals. That's extremely high. The typical solar wind dynamic pressures around Saturn are of 0.05 nanopascals, so it's quite large. Okay. So, well, basically, that's what we saw. We tried to show in different ways that Titan maybe is interacting with a transient structure, not with a pristine solar wind, and that's what results in its induced magnetosphere. And well, unfortunately, we only have this one observation to take this conclusion.
Fair.
But what we did also, that's in the discussion section, we took a catalog of around, I think, 1,300 Bow-Shock crossings from Cassini's era that was given to us by Matthew Cheng. He has his paper, I think it's already published with this catalog available for all. And well, he was kind enough to give to us while it was in preprint. So
nice, good.
thank you. Yeah.
There's a good
that catalog is, I mean, not in this table too, but what we did was this is this table too. What we did was take this large catalog of Bow-Shock crossings from Cassini, and we estimated the associated solar wind dynamic pressure and standoff distance of the Bow-Shock.
Yes.
Using one of the empirical models of the first section.
Okay. Yes.
And what we found is that from this large catalog, only about 78 Bow-Shock crossings showed enough compression to be past Titan's orbit.
Okay. Okay.
And then we went back to Elias Russo's catalog of solar energetic particle events and GCR periodic modulations. Okay. And we saw that I think almost 80% of these compressed Bow-Shock crossings could be linked to the presence of one of these extreme events. Okay. So what we take from this analysis is that it's most likely that if Titan, there's a chance of Titan being found in the solar wind. It's most likely that it will be interacting with an extreme space weather event that can either be an ICME or a co-rotating interaction region. Nice. So that's like the main result, maybe.
Very nice. Very, very nice. Beautiful, beautiful, beautiful. Very cool. Sophia, thank you so much for walking us through your very awesome APJ article. Let's see. So you hinted at it a little bit at a couple times, but let me just push on it. So where do you think we go with this over the next, let's say, couple of years? Unfortunately, there won't be another flyby. That was a one-off. But are there simulations that could be done? Are there other analogs maybe around other planets? Just sort of next steps, where do we go with this topic on figuring out the solar magnetic field interaction with planets in our solar system?
Yeah, well, actually, Laura Morales, that's one of the authors of this paper, is currently working with a French colleague of hers on simulations of Titan's environment with the parameters of the solar wind that we observe here. Cool. Okay. Yeah, to see if they can take more information on this interaction. That's quite unusual for Titan. And well, I think Niklas Edberg, that's another one of our co-authors, is interested in studying the impact on the ionosphere of Titan because of the presence of these solar energetic particles. Okay. And well, I don't know if we are gonna get to do this, but we were also interested in simulating the ICMEs because from we identified candidates around 1 astronomic units, but between stereo observations at 1 astronomic units and Cassini's observations at almost 10, there were no spacecraft in between that measured in situ these events. So we actually don't know what happens in the middle. Okay.
Well, we got to figure that out.
It would be nice.
Absolutely. Very good. Cool. All right. Well, I certainly look forward to seeing those works come out and progress on this topic move forward over the next couple of years. It'll be Very cool, Dr. Sophia.
Thank
Very
you.
nice. So thank you so much for talking about your very lovely article.
Thank you.
Thank you. And that will do, everyone. And I hope this made your astronomy day and your Saturn-Titan day just a little bit better. And we will see you on the next one. Bye-bye.
Bye.